Hello everyone, here's another Physics 30 example. This time we're into ray diagrams. And for example number 1 here we have a concave mirror. So we're asked to figure out something about a 20 centimeter tall object being placed in front of a concave mirror with a focal length of 80 centimeters. We're told that the virtual image is 133 centimeters from the mirror. And we need to determine the height of the image. Okay, so let's think about our ray diagram first of all. I always think this is really important just to situate the object, the image, the focal length relative to the either the lens or the mirror in this case, and that's really going to help you answer the question. Particularly, it's going to keep track of all those interpreted signs. So let's just go through it qualitatively. Without any values to start with. Let's go ahead and assume that the focal point is here. So this is F, and the F is 80 centimeters. Okay, so what would happen if we placed an object this side of the focal point? Okay, well, of course, what we need to do, we need to get our ruler out and we need to start drawing some rays. So I'm going to go ahead and do that. Let's take one ray from the top of the image to the mirror. Then, of course, it's going to reflect back through the focal point. Let me see if I can get this approximately right. There we go. It's going to come back this way. I'll draw a little arrow on there. And there we have it. Now, if we're interested in virtual images, we would be thinking about this virtual ray that would be on the other side of the mirror. Obviously, it's not a real ray of light because real rays of light can't pass through a silvered mirror. But we're going to put that in just to visualize because we know that it's a virtual image. Okay, next thing to do is, well, we can do several things, but I'm going to pass it through. I'm going to hit the center of the mirror. I'm going to go here, and this is going to reflect back perfectly symmetrically. So I'm going to approximately say it's going to go through this point here, which would be the same inverted height as the object at this position. So it's going to come back this way, and there we go. We can see that there. Now, what's really important here is looking at these rays. These are both real rays of light. Are they getting closer together? Yes, they are. So that means they're going to cross at some point, way over on this left side, way past the left side of the page here, and that's going to produce a real image. That's not what we're looking for here. We're looking for a virtual image. So right away, I can see that the positioning of the object in this place here, which I've randomly picked, can't be true. I will not get a virtual image if I'm this side of the focal point. So what if we move this object? Let's say we put it in front of the focal point. I'm just kind of playing around here. What if I put the object here? Okay, what's going to happen to the object to the rays? Well, same thing's going to happen. We're going to put our parallel ray in here, and that's going to reflect back through the focal point, so approximately here, and we're going to draw on our virtual image because we need that. That's what this question is telling us to do. It's going to go there. Now let's go ahead and do the central ray, this time coming back through the complete inverted opposite position that the object would be in if it was upside down. So this time it's going here, and then it's going to reflect back through this dot. If I can just align my ruler, there we go, approximately there, and this time the virtual image is going to be all the way up to here. Okay, so let's just extend my other virtual image or my other virtual ray, because I did not make that long enough. And again, I'm not doing this precisely, I'm just sort of guesstimating here. There it is. So these are the real rays going away, and notice that these are diverging. In other words, they will these will never intersect each other, provided we're on Euclidean geometry here. They will never intersect, which means you will never get a real image if your object is in front of the focal point. But you will, take a look up here, you will get a virtual image. So that's looking promising. Let's go ahead and put this in. Let's go ahead and put in a virtual image approximately here. Down we come. This is my virtual image. Okay, we're all happy with that. There we go. Now, just for scale, just to kind of rough this in so that we know what's going on. This here, I've said, is 80. Okay, which means this DI, this has to be, so this DI has to be greater than 80. And if I was to just sort of approximate it, let's say that this is 80, it's going to be approximate, well, it looks like, you know, double-ish. And again, bearing in mind that my diagram is not very good, it's not very to scale. So it's roughly double, which makes me sort of confident because this number here is, well, it's not far off of double. So anyway, I'm kind of hopeful for this situation. What's really important though is that we've noticed that the this side of the mirror is, when we're dealing with our signage, this is going to be in the negative value. So if we're talking about a focal length on this side of the mirror, then anything in here, because it's the other side of the mirror, would be a negative value. So negative focal length or negative images, these are all going to be negative values. So let's go ahead and look at crunch the numbers. We'll put it into our formula and see where we get to. Okay, well, what do we know? Well, we know that 1 over f is equal to 1 over di plus 1 over do. We also know, let's change colour, we know that magnification is hi over ho and negative di over do. And this negative value is an arbitrary number value in there to take care of any negatives in there, and we'll think about what that means as we go through. Before we do that, let's just qualitatively describe what sort of image we're looking for. Let's put it up here. We know that it needs to be larger. Okay, we're told that. It needs to be virtual, because we're told that in the question. And it's going to be upright. Okay, so this means that any magnification is going to be a positive value. Okay. All right. Okay, so what do I know? Let's just circle what I know. I know the focal length. I know this. I know the distance of the image. It's a negative value, negative 133. I also know the height of the object. I'm told that it's 20 centimeters. And that's about it. So height of the object, focal point, and di. That's the only thing I know. So clearly what I need to be doing here is solving for, I need to solve for do, and then that will bring me over here where I can now get the height of the image. Once I know do, oh, I forgot to circle that. I know this as well. I know the di. So once I get my dos, okay, hopefully you can see do here, do over here, I can then solve for the height. This is what I'm trying to find. Not interested in magnification. So let's put the values in. We'll first of all rearrange. So 1 over f minus 1 over di is going to give us the reciprocal of do. Okay, so do is, let's put these numbers in now. Do is going to be, let's go 1 over the focal. Oh, the focal point, sorry. The focal point is 80, so 1 over 80 minus 1 over, and this is important, negative 133. Okay, why negative 133? Well, remember, anything on this side of the mirror is a negative value. That's really important. That's going to give you different values otherwise. Okay, and then because we've taken care of the denominator there, we're going to have to call that a reciprocal. So DO is equal to, we can plug this into our calculator, is equal to 49.953, and I think there's some other values in there, and that's centimeters. Now, let's just see if that makes sense. 49 centimeters, well, the focal point is 80, so 49 would be just past the halfway, and that sort of makes sense, because remember, I roughed this in just by guesstimating, and it's a bit further over than probably what the real answer is, but that's given us a value of greater than 80, about double of 80, which is not bad for a sort of guess. So this seems good. Okay, let's keep going now. We need to now use the DO value to come over here, and then we're going to solve for the height of the image. So what have we got? Well, height of the image now. Let's just rearrange this. So the height of the image is going to be the negative DI, which I'm going to keep as a negative there, multiplied by the height of the object, which is a known value from the question, divided by this DO that I just calculated. So let's put the numbers in, and once again we're going to be very, very careful to keep this negative sign in. Notice what happens. The negative sign was arbitrarily part of the equation, and now it needs to stay. So we need to make sure it stays there. But remember, I've got a negative DI value because it's this other side of the lens, of the mirror. So that needs to be a negative and a negative. In other words, it's going to end up being a positive. And then my HO, the height of the object, is 20 centimeters, of course. And that is all over the distance of the object from the lens, which is 49.953. Okay, what do we get? Well, if you're careful with those negative signs and you treat this to be a positive 133 times 20 divided by 49.953, you're going to get the right answer, which is 5.325 something times 10 to the negative 1, times 10 to the 1, times 10 to the 1, which equals, if you put this in the normal language that we've been using so far, which is centimeters, which would be 53 decimal, and I've got 3 significant digits in my question, so 53.3 centimeters. That is the height of the image. Now let's just see if that kind of makes sense with my roughed in image. If this was 20 centimeters, over here now we have 20, 40, 60, like 70 odd, but remember that this was not very precise. I just guessed with this. So to me, 53 seems about right. And if I was to redraw this ray diagram with the object at 49, which would be about here, let's just put an actual approximation for where that would be. Well, this is 80, so it's going to be about here. This is where the image, the object really would be, and that would give us a different ray diagram, just slightly different. So there we have it. There's the algebra part. It tells us that we have a 53.3 centimeter image. Okay, second example here, we have an object being located 15 centimeters in front of a convex mirror. So previously we had the concave mirror going on. This time it's convexed. So this is what it looks like. We're looking at the light rays coming in from this side and diverging up this way, but we're calling this a convex mirror. We're given the radius of curvature, and then we're asked to find its magnification. So let's draw this ray diagram out and put in all the key bits and pieces that we definitely need here. Again, this is not to scale. I'm just roughing this in qualitatively just to see what's happening. So first up, the center of curvature is obviously, if we were to hypothetically extend this and make a circle, a complete circle, the would be the center of the circle. So let's call this C here. And we know from our ray diagrams that when we introduced this and derived our equations, the focal point is actually halfway. So the focal point is half, there we go, the focal point is the radius of curvature divided by 2. So this tells us our focal point, our focal distance. Our focal distance must be 5. Okay, so we're given that information from the question. Now we're told that the, well, we also know that the image, the object is 15 centimeters away. So I'm just going to sort of approximate that in. If this distance from here to here is 5, I'm going to say that the object itself is going to be way over here, 3 times further than the focal point. So just roughly, approximately, I'm going to put it here. Okay, so now I'm going to do my ray diagram. Here's my ruler. My ray comes in. It's going to come in parallel. Let's use blue. There it is. Blue coming in, hits the mirror here. It's going to then be reflected with its virtual ray going through the focal point. So that, oops, the real ray is going to go this way. The focused ray, sorry, the virtual ray, it's going to go through the focal point, just there. So let's just put these little arrows on, like this. Okay, that's the first one. Once again, we can do the second one. I'm going to do going through the middle, the exact midpoint on the principal axis, which means it's going to reflect back very symmetrically. It's going to come in like this, and then it's going to produce that symmetrical reflection. So if it comes in like this, I should put those arrows on. There we go. It's going to give us this symmetrical reflection here, and I can do the virtual rays on there. If I can just get my ruler straight, there it is. There's my ray, and my virtual ray goes off this way. There we go. There's my arrow. There's my arrow there. Okay, so where do they cross? Well, there we can see it's right there. So I'm going to get a tiny little arrow, or a tiny little object right here. So this gives me some qualitative things to work with. I should know that the image is going to be quite a bit smaller than the object. So it's going to be reduced, although it's upright. So let's go ahead and make these observations. We'll write them down. We now know that the object is going to be, let's put them up here. It's going to be virtual. It's virtual because there's no way these rays are going to cross, are they? We're going to get a crossing behind the mirror, which means it's virtual. It's going to be smaller, and it's going to be upright. Which, again, upright means I'm going to have a positive magnification. Okay, definitely smaller than 1, magnification of smaller than 1, but not a negative magnification. Okay, so let's put my equations in that I'm going to be working with. Obviously, I'm dealing with 1 over f is equal to 1 over dO plus 1 over di. And I'm also working with my magnification formula, hi over ho, hi-ho, and negative di over do. Which things do I know? Well, I know the focal point, the focal distance, it's 5 centimeters. I know the do, given in the question, 15 centimeters. And that's about it. I don't think I know anything else. No, that's all I know. So what I'm going to do is, so let's just circle, what do I know? I know this. Got that. What do I really, well, obviously I'm trying to find m, so I'm just going to solve for di. I'm going to solve for this. In other words, I'm going to solve for this, and I'm going to combine the two things together. So let's go ahead. Let's plug it in. I'm looking for a magnification that's positive and considerably less than 1. Okay, so that's just to have that in my mind. I want to know roughly what's going to happen. That's why these ray diagrams are so important. Okay, so let's put some numbers in. Well, first of all, I'm going to have 1 over f, I'll just rearrange this, minus 1 over dO is equal to 1 over di. So di is equal to 1 over, well, f is 5, minus dO is 15, and then that's going to be the reciprocal because I've taken care of that on the other side of the equation. And that gives me a value. I can put that in to my calculator. I'm going to get a value of negative 3.75. Oops, there we go, centimeters. Okay, now let's deal with this negative. It's negative 3.75. Now the negative here, if I get a negative distance, that means it's behind the mirror. So is this image behind the mirror? Well, yes, it is. Is it less than 5 centimeters? In other words, less than the focal length? Yes, it is. So this is looking good. I'm pretty happy with this negative 3.75. Let's bring it over to this side of the equation, my magnification equation. So the magnification is going to be equal to, now the negative sign is arbitrary, it's important, it's going to take care of lots of things for us, we want to keep it there. But I've also got a negative value, so negative 3.75, that's my di that I just calculated, divided by the dO, which is 15. Okay, and that's going to give us a magnification, if we put that in, of 0.25. And that's good news because that's what I was kind of looking for. In other words, it's going to be a positive magnification because it doesn't invert, but it's going to be much smaller than the height of the object.